Okay, today I'm going to discuss about a new topic which is called inner product space. So far we have discussed about vector spaces. And its properties, and we also talked about basis, dimension, and then we discussed about eigenvalues, eigenvectors, matrix representation of linear transformation, etc. But you know that in vector space, if it is a kind of algebraic structure where the set, first of all, is a non-empty set, okay, and that particular set needs to be closed under vector addition and needs to be closed under scalar multiplication. So if I give you a structure, say for example, V, then an operation plus, and then an operation dot in this manner. And if I say that this is a kind of, no, I'm not going to use this notation because there will be some trouble using this notation now. Suppose I'm giving you this structure, okay, and I'm saying that it is a vector space, then you already know that the first thing that comes to your mind is that number one, V is non-empty set, and V is closed with respect to addition. Not just any addition, with respect to vector addition. And number three, V is closed with respect to scalar multiplication. These are the three fundamental things that come to our mind when we talk about vector spaces. And then some other properties that the elements of the vector space satisfy. But if you look at the properties, you'll see that we have properties like commutativity, we have properties like associativity with respect to both with respect to addition, we have properties like algebraic, additive identity, and we have properties like additive inverse. So in all these four properties, we are fixing ourselves to vector addition kind of thing. We are concentrating on this symbol. Okay, the two vectors are getting added with one another. And the remaining properties where we actually connect a scalar with a vector. So first of all, we start with the closedness of the scalar multiplication, and then we say the multiplicative identity kind of thing is there, which is an element of the field. And when it is getting multiplied by the vector of the vector space, then the same element comes. And then we try to connect the addition with multiplication, like we use this sort of result. I mean to say, we use kind of result where you see that the scalar is getting multiplied by the vector. Then we use this thing like this, a plus b dot x, which is a dot x plus b dot x. And also we try to connect this dot and addition plus with in the following manner. We write it like this. Probably you can recall all these properties that we discussed earlier. So sometimes
yes, what we VS1 to VS8. Yes, sir. VS1 to VS8.
VS1 to VS8. But what is happening over here that you carefully observe, sometimes we try to connect to scalar multiplication, this dot with one another. Here this dot comes from the field, and here this plus is connected to this dot, where this plus comes from the field operation, This dot is from the vector operation. This dot is from the vector operation. Here, this plus is from the vector operation. It is the vector addition. And these are the vectors. So this becomes the vector addition. Okay. But neither of these properties, we use the product of two vectors. The product of the two vectors have not been introduced in any properties of the vector spaces. So now it is a time to introduce that feature into the algebraic structure, and we are going to discuss another space which is a special type of vector space known as inner product space. Okay, where the product of the two vectors will be introduced. Now, how do we define inner product space? Let's define it first of all. Let capital V be a vector space over the field F. Okay, first of all, it is a vector space over the field F, and since it is a vector space, it satisfies all the 8 properties. All the 8 properties are automatically satisfied. So the definition of inner product space starts with this first assumption that the set must be a vector space over some field F. Remember this. Then an inner product on V is defined in the following manner. It is actually a function. It is actually a function that assigns to every ordered pair of vectors, X and Y in V, a scalar quantity in F. And this scalar quantity is denoted by this notation X, Y. That's why I say that I cannot use triangular brackets now. It's preserved for denoting the inner product between two vectors. Okay, so in other words, we can say that this notation where I consider two vectors which are being denoted by dot, separated by comma, put inside a triangle. This notation is a kind of this is actually what is known as inner product, which is a function whose domain is V cross V, and it gives your image in the field of scalars. So it is a function of this form. We choose two elements, X and Y from V. We choose X from V and Y from V, and we put it over here in this position, dot and dot, and we get a number. So inner product is a number, and there, since this number is a number, it belongs to the set. It is a number. It belongs to the set of field. Is a set of scalars, which is called field. Okay. Now, if F is R, we get real inner product space if F is C, we get complex inner product space. Now, what are the properties? This is the notation, okay, for denoting the inner product between two vectors. it will satisfy certain properties also, such that for all x comma y, z also in V, and all C in F, the following properties hold. The following properties hold. Okay. What are the properties? Number A, first property is this. If I consider x plus z, its inner product is taken with y. We get x comma y plus z comma y. This is the first property. So inner product is linear in its first argument. So you see, if I consider this triangular bracket and this element and that element, this is called the first component. And this is called the second component. Yeah, Shomata, say. Somata raised her hand. Want to say something?
No, sir, it was my mistake.
Okay, so if I consider a triangular bracket, if I put two dots separated, okay, then Arif Ali wants to say something.
Yes, sir. The sign that you have put in the property number A should be different, right? Because x and z are vector spaces. Sir, the plus sign that you have put in the property number A, the first property, is it correct? Means x and z are vector spaces.
Yes, actually you are right. Very good, but I am supposed to write this symbol over here because this is the addition between the two vectors, and this symbol is the plus, because simple plus, because these are the scalar numbers. Okay. This plus is just a plus from the field, and this plus is the plus from the set of that vector addition, this plus. But for the sake of, because right now at this moment, you are very much well aware of which plus is which one. I mean, when we talk about the addition between the two vectors, then we know that, yeah, these are the vectors and we are actually adding them. And you also are conscious about addition of two numbers. We can understand the difference between the two. So at this moment, these terminologies will not be required at all. Once it is implied from your understanding, once you understand this from its, from this itself, then you need not write it, you need not emphasize it again and again. Okay, so everybody understands that, yeah, these are the addition of two vectors and these are the addition of two scalar quantities. But those, when you are the beginners, those who are beginners and learning vector space for the first time and not well aware of the algebraic structure at all, they do not know do not know how to differentiate between the structure of vectors and structure of scalars. To those learners, we often use different symbols to always make them conscious that, yeah, when you are adding two vectors, be cautious. When you are adding two numbers, be cautious. Try to identify when you are adding two vectors and when you are adding two numbers. Those are for beginners. But at this moment, after all these chapters, you are well connected with this. So I shall not recommend to use different notations for these additions, because that's why, although in my mind, I know that this plus is something different, I'm just simply writing it as plus. Okay, so, but don't confuse, don't think that this is my mistake. I'm not mistakenly doing this. I'm intentionally doing this, because when a person does higher mathematics, then if we use different symbols, sometimes things become clumsy. So once it is understood from its context, then we just appreciate it and we use what we are comfortable with. Got my point?
Yes, sir, got it. Thank you.
Yeah, okay. Now this is the first property. Oh, what I was talking, that this in triangular bracket, this is a symbol of inner product between the two vectors, and therefore this is a vector, this is a vector. We are taking the inner product of these two, and this part which is preceding the sign comma is the first component, and this part which is succeeding comma is called the second component. So from this property, we see that this inner product is linear in its first argument. We can say that inner product is linear in its first component. In its first component. This is the first property that needs to be satisfied. Second property is if we multiply a scalar by a vector, and obviously be careful that this multiplication is this one. Although since you have raised the doubt, so I am just clarifying again and again, but I shall not be using it while doing problems. Remember, so if I consider this particular thing inner product, then simply it becomes C comes outside and we multiply this number by C. This product is just simple dot. Number C is something else, something different. And we know it, it's nothing new to us. If we take it to inner product between two numbers, and if I put a bar over there, then it simply becomes inner product of y and x. This bar actually denotes complex conjugation. Niladri wants to say something.
Sir, if we take x comma cy, then the c will come outside in that case also.
X comma, no, something will happen. It is a theorem. C will not come. It's C will change to something else. If I take what you are asking, that if I take x comma cy, what will happen? Will it be C into x comma y? The answer is no. Something else will happen that we'll be discussing later on. So remember this point. It is also, thank you so much. It is a very important point. And number D is if I take inner product between the two numbers, same vectors, then it is always positive. Okay. If x not equal to 0. If x is 0, I mean, if you ask me what will happen if x equal to 0, then it is actually a theorem, a simple theorem. It says that inner product between the two numbers is 0 when x equal to 0. It is a trivial case. Okay, so it is not included in the property itself. So therefore, we get this type of thing. So inner product is always positive. Inner product is a number and it is always positive. Okay. Inner product has a special name. Inner product has a special name, which I'm going to introduce later after solving a particular problem. Okay. Remember this particular thing is important. This is called the complex conjugation, because you know what complex conjugation is. A plus bi, if a plus bi is there, and if I take the complex conjugation of this, it becomes a minus bi. Remember this. That is happening over here. So these are the properties that are which when satisfied, we'll call this particular function as inner product. And if this inner product satisfies these properties, we simply say that the vector space that we are considering and on which the inner product is defined becomes inner product space. The inner product space is also a kind of vector space. Okay, and also I shall try to write an important note over here at this point, which will not be required for your purpose, for your syllabus, but those who are willing, those computer science engineering students who are willing to pursue quantum computing in their 7th semester course, for them I am writing this note. Remember, a complex, rather I must say, finite dimensional complex vector space with inner product defined in it is called Hilbert space. It's called Hilbert space. Remember, many such spaces are there. What is the difference between set and space? Set is just consisting of some elements. Okay, two sets can be connected by operations like union, intersection, and difference and complement. Space is something which is different from set. And space is a kind of set where some algebraic operations are defined. The mother set is a vector space, okay, where we actually considered some properties. We define the field, and you know the elements of the vector space are constructed from by choosing elements from field. Vector space is the bigger set. Hilbert space is just a part of it. So the diagram will look like this. For example, if this is my vector space V, then this is my inner product space. Say, let's denote this by, what shall I write? Suppose this is not this notation I'm using. Then this is the inner product space I, and this becomes your Hilbert space H. Okay, so this is
not visible.
Okay, I'm right. I'm drawing it properly. Just a minute. I'm saying that these things are not
page
required.
one,
huh?
Page 2 is not visible.
Which one?
So page 1 is visible, but page 2 is not visible.
Oh, I have not gone to page 2. Have you written this definition? This note, the Hilbert space definition. Is it visible?
Yes, sir. It is visible.
Okay, I'm saying that if this is the vector space structure, then inside the vector space structure we have another structure which is the inner product space. Inside inner product space we have another structure which is called the Hilbert space. So this H is the subset of I. This I is the subset. Now H is not actually subset of I. H becomes I becomes H when we are considering F to be C. If F is C, if it is a complex inner product space, finite dimensional, of course, then we consider this to be, and on which inner product is defined, we consider this to be Hilbert space. Now, why this is important? It is important because entire quantum mechanics is built upon Hilbert space. Quantum mechanics have been studied on this particular space, which is called Hilbert space. So therefore it is important. And since quantum mechanics is defined on Hilbert space, so quantum computing is done on Hilbert space, quantum information is done on Hilbert space. We shall not be using these things anymore over here in this particular class. Let's leave it for 7th semester course. Now let's proceed. So these are the 4 properties. If when satisfied, we say the vector space to be inner product space. Okay. I'm going to the next page. Now, suppose I'm considering some vectors. Let V1, V2, ... Vn be small n vectors, okay, which are taken from V, and A1, A2, ... An be n scalars taken from the field F. Okay, suppose I'm choosing in this manner. Then let us construct the linear combination of these n vectors as follows. Okay, linear combination is like this. We are considering it as summation I goes from 1 to n ai vi, which means a1 v1 a2 v2 ... an vn. Now if we take inner product of summation ai vi, I goes from 1 to n with y, yes, with y, then what we get? We get inner product summation I goes from 1 to n ai vi comma y, which is a1 v1 plus a2 v2 plus an vn comma y. And now you are going to use the properties that have been written in the first page. The first page, let's look at the properties. I'm going to use property number A first of all, and then I'm going to use property number B. If I use property A, then we get, since the inner product is linear in its first component, remember, of course, these sums, plus, 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 these sums are vector sums. Remember this, it is implied. So if I use the property, we'll get a1 v1 y plus, this is the field plus, a2 v2 y plus dot 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 plus an vn y. Okay, and if I use the property 2, the scalar will come outside. We'll get v1 y plus a2 gets common, v2 y plus dot 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 plus an gets common, and we get n into vn y, which can be written again as summation I goes from 1 to n ai vi comma y. A very important result. Remember, star. So what it says also that it is also a kind of way to understand that inner product is linear in its first component. Okay. All of you write your student IDs in the, roll numbers in the chat box. You have got your roll numbers, or you can write your student IDs also if you can, if you want. I have been taking the attendance in terms of student IDs, so you write student IDs. Don't use university roll number now. Okay, so this is the thing. Probably you have understood. Now I am going to show you a special example where I am going to show you that with respect to a typical operation, a particular vector space becomes inner product space. So let's choose this example first of all. So question is, you are all acquainted with the vector space Fn. We know that what kind of vector space it denotes. F is the field. So if Rn, if F equals to R, then it is n-dimensional vector space. If n equals to 2, it is 2-dimensional vector space, and so on. And the elements of Fn are the n tuples. Okay, so I'm choosing this as the vector space, which is defined over the field F. You also know that very well from the first chapter. Let V equals to Fn. So it is a vector space. Define for x is equal to a1, a2, dot, 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 an belonging to Fn, and y is equal to b1, b2, dot, 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 bn belonging to Fn, and define for x is for x belonging to Fn and y belongs to Fn, the following number as if I take this symbol if I define the inner product as follows, okay, then we want to show that under this operation, Fn is an inner product space. Fn is an inner product space. We want to show it. This is the first problem that I'm going to discuss. 56 participants are there and 48 only put their attendance. Others, please do so quickly. We want to show that this operation is an inner product. This operation is a kind of inner product, and therefore, hence, Fn is an inner product space under the operation. The operation is defined in the following manner. Okay, so we are going to check all the properties for this particular operation, one after another. So let's start this problem. Probably I'll not be able to finish it. Yes. Want to say something? Yes, yes. Tell.
That is BI bar.
BI bar. BI bar. It is BI bar.
Okay.
Okay. So probably I'll not be able to finish all the able to show you all the properties in the first session. So we'll continue in the next session. So I'm going on to the next page. If you have not copied, please take a screenshot. Solution. Let's start the problem and then we'll move on to the next session and we'll continue. First, we need to show the property 1, for which we take 3 elements from Fn. This is the one element. Y equals to B1, B2, Bn is the second element. Z is equal to C1, C2, Cn is the third element. Now, X plus Z, comma Y means A1, A2, An plus B1, B2, Bn. Sorry, not B1. Extremely sorry. It should be X plus Z, means it should be C1, C2, Cn. And we are going to take the inner product of this with B1, B2, Bn. Now we know how n tuples are added with one another. So we write it as A1 plus C1, A2 plus C2, An plus Cn. Now when I am multiplying A1 with C1, sorry, when I'm adding A1 with C1, then this addition plus is scalar addition, remember. These are not the vector additions. So we get this. And suppose we are considering AI plus CI to be another number, say DI. So actually what we are getting D1, D2, Dn, comma B1, B2, Bn. Now, what you can do, you can, this inner product is defined. How have you defined the inner product? Just look at this. Summation I goes from 1 to n, Ai, Bi bar. So that would be what? That would be my inner product is X, comma Y is summation I goes from 1 to n, Ai, Bi bar. The component, first component is taken and second component's complex conjugation is taken. So we write D1, B1 bar plus D2, B2 bar plus plus Dn, Bn bar. Now let's resubstitute this. A1 plus C1 into B1 bar plus A2 plus C2 into B2 bar plus plus An plus Cn into Bn bar. Now you can multiply the numbers. A1 B1 bar plus A2 B2 bar plus dot 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 plus AN BN bar. We can take them together because the scalars are commutative and we can keep them together. C1 B1 bar, C2 B2 bar, Cn Bn bar, because they are commutative, and therefore it is nothing but summation I goes from 1 to n